grabbing real quick. There we go. And is my screen shared? It's not, is it? Let's do that really quick. Let's make a board. All right, so we had been talking about separable differential equations. Okay, so first order, right? So first order just meant, remember that we have a lot of terminology that's floating around here, right? So we are going to focus our attention for the remainder of the chapter on what are called linear first order. Well, you can change the order in which you say those, but linear first order uh, ordinary differential equations, right? We were talking about ones that were also, in addition to those terms, separable, which we'll go over in just a second. But we're going to focus our attention after we talk about separable differential equations for just a couple more minutes on not necessarily separable first order linear ordinary differential equations, okay? And remember that all that terminology is important in the long run, but you don't need to know all that terminology for FP2 exam. You really just need to know how to solve them, right? So it might be, I think the terminology is helpful just remembering what to look for and what to use as your technique, but the terminology is not required, right? They're never going to say, what does it mean to have a linear first order separable differential equation, so on and so forth, right? Anyway, okay, so separable differential equations, just to recap. So separable diffeqs, or I'll call them ODEs. Remember that ODE stands for ordinary differential equation. Oh no, I hate when this happens. I've got to close out my live board and reopen it. Okie doke, let's see. So separable ODEs. These are things that are always in the form dy dx equals f of y times g of x. And we had a procedure that we went through to solve these ordinary differential equations, which was to first do what was called the separation of variables. And the separation of variables basically just meant you divide both sides by f of y. You get 1 over f of y dy dx equals g of x. And then we integrate. That was our second step, right? We integrated with respect to x. So we take the integral with respect to x of both sides. And what we effectively get is on the right or the left side of the equation, we get a y integral, right? So this turns into a y integral by chain rule or by u substitution, whichever one you want to call it. So we get the integral of 1 over f of y dy equals integral of g of x dx. And this could, as long as these integrals are solvable, meaning that, they're in a form that you can actually find the antiderivative of, then you can find the general solution, giving you a plus c, and you can find the particular solution if you have some initial conditions, right? So that basically sums up what we did yesterday. Let's do an example to refresh our memories. Let's try one that's actually really a nice example. It's actually relatively simple to solve, but it'll give us an idea of how this stuff is applicable. So let's say that given a certain we're gonna talk about an actual situation that might arise in a scientific experiment or in a lab, right? So say we've got a bacteria. This is always the typical differential equations, the first typical differential equations problem that you do, or one of the first ones. So we've got a bacteria that, let's say, has got a growth rate that's proportional to the population. And this is a pretty reasonable situation to describe because you're saying, all right, so say I've got 5 members of a population, and each one of those has, a reproductive rate of K, let's say. Well, then if there's 5 of them, the reproductive rate overall should be 5K, right? So it's proportional to the population. That actually makes sense. So let's write that down in English. So we'll say a certain bacteria or a certain population. I'll say bacteria right now because it's one of the typical ones that's used. A certain bacteria has a growth rate proportional to its population, right? And we'll say that the proportionality constant, that has a proportionality constant of K.
Sir,
Yes.
usually they use bacteria because they're easier to model, right? because they have like a simpler.
Right. Yeah. So bacteria is a good one to use. Well, it's not only that it's simpler to model, it is, that's absolutely right, but it's also because they actually are going to be somewhat accurately modeled by this, right? We would also have to, if we wanted to come up with a more accurate model, we'd have to have a growth rate and a death rate, right? So because bacteria don't live forever, right? So you'd have to have some sort of thing that accounts for the death rate as well. And you can have all sorts of parameters that go in there to make the growth rate fluctuate in certain circumstances, right? But we're doing the most simplistic model. But yeah, bacteria is a good one to use because it's pretty simple, right? Or at least you can come up with a not necessarily totally unrealistic example relatively simply. Yes, that's right. So what we're going to say is the population at any given time, right? So the population at any given time is given by the letter P. So population at any given time is, we'll say P, right? It looks like just I, but it's actually supposed to be a P. Is P. And so what this is going to tell us, if we think about this for a second, what is the growth rate? Well, this tells us that the growth rate, and so the growth rate is given by a differential equation, and the differential equation is basically, well, the rate of change of P, let me make that a little bit nicer looking. The rate of change of P with respect to time, in other words, the time derivative of the population, is just equal to the growth rate, which we said was proportional to the population. So this is just going to be K times P.
Could instead of using instead of using the use like the triangle that indicates rate of change,
The
or just
delta?
meaning a different
Yeah,
thing? Yeah.
yeah. No, yeah, it does. The only thing that's different, so you could say like delta P over delta T equals like KP. The only problem with this is that this is not continuous, right? So this would be an approximation. This would be like saying if you've got a curve, let's say this is the population, right? This is like saying take a point here, take a point here, and draw a straight line through it, right? Whereas this is referring to the tangent line. So this is more this one here that's supposed to be an arrow. That thing is referring to an instantaneous rate of change, whereas this one is referring to an approximation. Does that make sense?
And so
Yes.
P is gonna be a function of time, right?
Yes. Yeah. P is going to be a function of time, but we're going to find that function of time right now explicitly. Okay. So here's what we're going to do. We're going to solve this differential equation. And we can also even say, we'll say like, um, assume that at time 0, so at time 0, we have a population of P0. Or I can just write, we have P equals P0. So like P of 0 equals some constant, P0, right? This is just some constant. The initial population. Okay? So here's what's going to happen when we solve this. This is separable, right? We have dp dt equals kp. Remember that k here is just a constant, right? And so to separate the variables here, we have to get all the p terms on one side and all the t terms on the other side. Of course, there aren't any t terms, but that's fine. We can just think of it as being t to the power of 0, right? So we're going to divide both sides by p. We're going to get 1 over p dp dt equals just regular old k, right? K is a constant here. You got to remember that. So once we have that, we're ready to integrate, right? This was our step 1. We've separated our variables now. Our second step is to do the integral. So we take the integral with respect to t of both sides. 1 over p dp dt dt equals integral of k dt. So the integral on the left-hand side, of course, becomes a p integral. So we just 1 over p dp equals integral of k dt. And now what's the integral of 1 over p dp?
Natural logarithm of p.
Yes, you're having problems with your mic today, aren't you?
Yeah, it's going wild.
Anyway, it's fine. As long as you get the message across, who cares, right? So it's natural log of p. Remember that I'm being uncareful about putting absolute value here. we can actually, if we really wanted to, we can make a physical argument for why that won't matter here. And the physical argument would be, well, it's not going to ever be a negative population, right? You're not going to have a negative population. That doesn't make any physical sense. So who cares about putting the absolute value, right? All right, so that's going to be equal to, well, the integral of k with respect to t, since k is just a constant, is just kt. And then remember that we've got to add a constant of integration, but we can just add it to one side. So we're going to add it here. So we have natural log of p is equal to kt plus c, right? It's taking a second. There we go. And so, of course, we wanted to solve for p, since we would ideally like to find, the population at any given time. We just, of course, take e to the power of both sides, and we end up with p is equal to e to the kt plus c. And then what we can do is we can rearrange this as writing e to the power of c, e to the power of kt, right, using exponent rules. And then remember yesterday we were saying let this equal like some other constant, a e to the kt, right? Just say like if we let a equal e to the power of c, then we can easily write it in that new form, right? Okie doke. So now that we've got this, we've got p of t equals a e to the kt. Is there a question?
No, it's my mic going on and
okay.
off by itself.
Okay. All right, so we've got this form. We can now find our particular solution, right? This is our general solution, which, by the way, you'll probably see me do this a lot, where I'll just write like g.s. That's a general solution. But to find our particular solution, we've got to apply our initial condition, which tells us that
One more question.
Yeah.
What is a? Let a equals e
we're
to the power.
letting it's just we're defining a new constant, right? Because c might be 15, but it also might be natural log of 2. And so if a is just e to the power of c, it just makes our math a little bit easier. Okay.
Also,
Yeah.
sir, like just today we just did like exponentials and did how the like transformations of a and multiplying the c. So this is very familiar.
Awesome. That's perfect. That's good to hear. That's good timing then. Coincidental, but good timing. Okie doke. So then if we apply our initial condition, we know that p of 0 has to equal p0, which of course is just some arbitrary constant as well. We're just going to do a renaming of constants here, basically. And if we plug 0 into our solution, we get a times e to the power of 0, which is of course just a. So we see that p of t, right, is actually just p of 0, p0, e to the power of kt, right? And so the only reason I even defined p0 at all was so that we could have a physical interpretation of what that constant meant, right? It's our initial value. It's what our population starts out with. And of course, there are some conditions here to consider. So if k, or you guys could tell me probably if you've started studying exponentials, if k is less than 0, we have what? What case would that be?
You have start making it smaller and smaller.
Yeah, this is called exponential decay. This is called exponential decay, right? The population's getting smaller. And if you've got k greater than 0, of course, now we have exponential growth. Exponential growth. All right. So interestingly, there's some real world applications to this that you guys are experiencing right now. So think about a virus, right? How does a virus spread? And keep in mind that this is a very simplistic model. Viruses are actually much more nuanced than this. But you can think of the basic principle of a virus as being exactly like this, right? If there are 5 people, the 5 of you, if all 5 of you have the virus, and you all have, let's say, on average, the same likelihood or the same possibility of infecting somebody else, it's like you are all members of a population with a growth rate, and you can then each infect somebody else, right? And so you could say that in a really simplistic model, a virus has a growth rate that's proportional to the population of infected people, right? And so that's why viruses spread so quickly, because if the growth rate is greater than 0, then you have essentially, at least at the beginning, exponential growth, right? So this is this is a very simple model that we've done here, and of course, real models are vastly more complicated. But just this simple model gives us insight into how important differential equations actually are for modeling the real world, right? Okay. How does this feel? Is this okay?
Yeah.
Yes, sir.
Awesome. Fernando, is it class change right now?
It's yeah, and it's also climate here.
It's also what?
Fer, Fer, are you in the library?
Hello, sir. Good afternoon.
Yeah. Yes, I'm basically at
Hello.
work.
I lived you in your class. Bye.
Who is that?
That's Jaime.
Oh, hi, Jaime. How's it going?
Mute your
No, he's
microphone.
already gone.
Oh, he's already gone. Okay.
He says bye.
Jaime, that comment was perfect. I love that. Alrighty. Okay, so we've gotten a decent idea of how this stuff works. There's a million different situations that I could come up with that would show you how this stuff is pretty important, right? How differential equations are actually modeled in the real world. I think that you guys in P4, when you finally get to this, you'll talk about logistic growth, which is actually much more similar to how viruses work. Let me see if I can actually find a good logistic model. Real quick, we can maybe solve that as another quick example.
So since we started this topic, I can't stop seeing things now like differential equations,
That's great.
like
That's exactly what you should be
acceleration, energy
doing.
transfer. Like especially in physics and in physica, nearly everything is.
Oh yeah, absolutely. And I mean, like I said yesterday, it really is not too much of an exaggeration to say that basically everything in physics is a differential equation. You can even think of physics itself as being like the study of differential equations, right? That's a little bit of a simplification, but it's true, right? So let's see real quick. If I can find this quickly, we can maybe solve it. It's like a correction to the exponential model, but I can only find the solutions. I want to find the differential equation. I think I know it, but I just don't want to make sure. I want to make sure that I get it in the right format. Okay, here it is. All right, so let's say we have this one actually is a much better model for viruses, right? So viruses are actually, there's still more nuanced, but this is a much better model. Let's just do it really quick. So we'll say a correction to the exponential model, is called the logistic model. The logistic model like this, and it's given by the differential equation dp dt equals, let's see, I want to use the terminology that we were using last time, kp, but then we've got this factor here, right? 1 minus p over k, k and k. Ugh, that's bad. All right, here I'll use, instead of k, I'll use pm for population max, right? So, all right, so what this is it's exactly this. If you cover up, I can't do it, of course, in front of you guys because usually I would have the blackboard and I could do this with my hands. But if you forget that set of brackets is there, for example, or for a second, what you have is the original equation that we solved, right? It's the regular exponential curve. dp dt is equal to kp. But what you're doing now is you're weighting it by this factor that goes down, it gets closer to 0 the closer p gets to pm, where pm is like the total, or I'll do, instead of pm, I'll do pt, where pt is like the total population, right? So what this means is, if you think about viruses is a good way of picturing this model. What it means is that, yes, the virus growth rate is proportional to the population, but the closer the population gets to the total population, right, the slower the rate gets, right?
Oh.
And that's because you can't infect more than the total population. That'd be impossible, right? So you're like maxing out at the total population.
So basically,
Hey, sir.
so basically,
Who's that?
you're getting like this slow growth, then you're exponential growth, and then you're getting slower and slower, right?
That's exactly right. Yeah. So what you're going to
And
see,
does it create like an asymptote?
it does. That's exactly right. So what we're going to see is that we get locally exponential growth, right? Which means that at the beginning, and Peter and Alex, I don't remember if you did this project or not, but Peter, you did this project in computer science last year, and you'll recognize the curve that we get. But what you're going to essentially see is that at the beginning, And for a while, you do get true exponential growth, right? It's almost identical in its derivative, right? The value will be very similar. But the closer your population gets to being totally infected, or, doesn't have to be necessarily viruses, but viruses is a good one, or you get close to what's called the carrying capacity for a habitat, let's say, if you're talking about bacterial growth, a bacteria can only grow so much, right? You can't have bacteria grow forever. A certain, community that they live in, a certain habitat might only have a finite amount of resources. And so that's going to be called the carrying capacity. So the closer you get to that, the less exponential you get, and you'll actually get this
so it's
asymptotic behavior.
more of a log curve.
Exactly. It is. That's exactly what it is, right?
Yep.
That's exactly what it is.
Is that true that the most, how to say, the biggest degree of people having like illness will be in the middle of the population of the, for example,
The highest growth rate. Yes.
Yeah,
Yeah,
the
that's
highest
true.
growth.
Yeah, that's absolutely true. It's not necessarily the largest number of people infected per unit time will be right in the middle. Yeah, that's exactly right. Yeah.
Okay.
Okay. So let's solve this real quick, because this is a separable differential equation. This is something that we can technically solve, right? The algebra is a little messy, but I'll just go through it relatively quickly, because it's just algebra that we have to do here. So this is separable in the sense that we can take all the p terms to one side and all the t terms to one side. So we would divide both sides by 1 over p, 1 minus p over pt, like this, dp dt equals k, right? And then we'd integrate.
Because PT is just a constant, right?
dp is just a constant, right? It's the total population. So you can think of, if we're talking about the virus, right, because it's a very relevant thing, then we can think of PT as being 7 billion, right? More or less. Okay, so integrating, of course, turns this left side integral into a dp integral. So we have 1 over p 1 minus p over pt. dp equals, I'll go ahead and just solve this
But this
one, right?
is not a realistic model, right? Because like in real
Well,
life, there's many
So
more.
yeah, there are vastly many more variables to consider, right? So one thing to consider would be how many people are dying because of this virus. Can people get reinfected from this virus? Are people being quarantined? That's actually something that you can throw into a differential equation to make your model more accurate. You have the rate of recovery, the rate of reintroduction to the population. In other words, how long does it take for somebody to get reinfected, if they can get reinfected, right? All these different parameters will vastly change what the model looks like. There's a differential equation model that was done in Wuhan very shortly after the coronavirus, went global, that used one of these types of models. It's called an SIER blah 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 model, right? And they were able to accurately predict down to like a margin of error of only a couple hundred or a couple thousand cases how many people in China would be infected given the certain conditions, and they were accurate. It was very, very accurate. And so this is like the standard methodology for finding models like this. And it's not just viruses, it's just many situations, right? But of course, you've got statistical parameters that you got to include, so on and so forth. We're not getting anywhere near that right now. This is just a modification to the exponential curve that gives us a much more realistic basic model for growth of a population, right? Okay, so I went ahead and solved the right integral, because might as well, right? And the left integral would be solved by partial fraction decomposition. So we would say this is 1 over p, or a over p, plus b over 1 minus p over pt, okay? Which of course we can modify that b term to just be, well, no, I won't do that. Don't worry about it. So multiplying through, so we get this is a times 1 minus p over pt plus bp has to equal 1, right? So this is all over p 1 minus p over pt, etc., right? Blah, blah, blah. And so, of course, we're going to plug in our values. So when p is equal to 0, we'd have a times 1 minus, or no, just 1. A times 1 equals 1, which, of course, is a very difficult equation to solve. So a equals 1. And then we have p equals pt. When p is equal to pt, of course, the a term drops out, and we get b is equal to 1 over pt. Right? Not too bad. So far, so good. And so we're just solving the equations, or the integrals, 1 over p, let's see, plus, I'll just go ahead and simplify it, 1 over pt minus p, all dp. Do you guys see how I got that second fraction?
Why is p equal to 0?
Oh, I'm doing partial fractions. So remember, I can choose whatever values of p I
I
want.
always get mixed up. Okay, yeah, sure.
Do you guys see
Yes,
how I...
you just multiply the denominator by pt.
Yeah, I did. Instead of just putting in, I did 1 over pt for b, and instead of just doing it as 1 over pt over a bunch of stuff, I just multiplied the bottom by pt, right? So it gives me this simplified integral. These integrals are relatively easy to solve. I'll just say, instead of going through all the u substitution here, unless you guys specifically want me to, I'm just going to write out the solution. This is going to give us natural log of p, which again, remember, we don't really care if this is absolute value because we're not going to have a negative population. And here we'd have a negative natural log of pt minus p, which is also going to always be positive because p can never be bigger than pt, right?
So why is it minus?
Because of the minus p in the denominator.
How does that affect it?
Let me show you that real quick. So if I have, I'll just do a side note here. Let's just try and solve the integral 1 over a minus x dx, right? Where a is any constant. Well, doing a u substitution would lead us to u is equal to a minus x, du dx is equal to minus 1, and so we get dx is minus du, and so we get the integral, well, I'll write it up there. The integral becomes minus the integral of 1 over u du. Make sense?
Yes.
Alrighty, so we get, this can also, of course, be simplified using properties of natural logs. So this is natural log of p over pt minus p. And this, we said, was equal to, well, this thing right here, right? kt plus c. So now we're left with natural log of p over pt minus p equals kt plus c. And what we're going to do is we're going to do basically the same steps that we did before for solving for p. We're going to have a little bit more algebra that's going to be involved here, right? So we're going to take e to the power of both sides. I'm going to separate this off so we know it's a separate thought. Okay, so we've got p over pt. Is there a question or comment? No?
No, it's my
Just your
mic
mic.
again.
Oh, you had your stupid mic. So we have e to the kt. I'll go ahead, and if this is okay with you guys, I'm just going to go ahead and say this is a e to the kt, right? If we let a equal e to the c. This is exactly what we did last time. Let me know if I'm skipping anything inappropriately or something that's not making you happy.
Just one question.
Yes.
What would the C be like? What would it represent in the model? And what would the constant be?
So you can think of it as being,
because like the constant of growth is K, right?
The constant of growth is K. I actually wouldn't interpret C by itself. I would wait until I have my final solution to the equation and then interpret whatever my constant has become. Does that make sense?
Okay. Yeah.
So, because in this particular case, I think what we'll see if we set like P0 equal to something, like equal to P sub 0, we're going to see that A is like a combination of P0 and constants, I believe, right? Depends on how I set up the original model. I think in this particular way, we have it's not that pretty. So it's not that easy to interpret just right off the bat. Okay, so we want to make P the subject here. So we're going to multiply both sides by PT minus P. Okay, so this is going to be P equals a e to the kt times pt minus p, which we're going to expand those brackets. It's going to give us p equals pt a e to the kt minus p a e to the kt. We're going to get the p terms on one side, so p plus p a e to the kt equals pt a e to the kt. Sorry that I'm doing this kind of monotonously, but whatever. And we get, factoring out the p, we get p times 1 plus a e to the kt equals blah, 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 pt a e to the kt. And then we divide, right? So we get p equals pta e to the kt divided by 1 plus e to the a e to the kt. Okay, so that's our solution to our equation. And what you'll notice is if we were to imagine that k is positive, right? So just imagine that k is positive. We have a growth situation. So if k is positive, what's going to happen when t gets really, 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 really big is that we're going to approximate, it's going to get closer and closer to pt, right? So I'll say if k is positive and t goes to infinity or gets really big, we'll say just goes to big, right? Then P is going to go to PT, right? Because the top part is going to be approximately PT A e to the KT. And on the bottom, that one is not going to matter a whole lot, right? The one's going to be relatively insignificant. So we end up getting closer to just PT A e to the KT over A e to the KT, and those terms cancel each other out, right? And so what this is telling us is that locally at the beginning, for very small values of t, we have exponential growth, but as we go farther and farther out, we get closer and closer to just being a constant horizontal line.
Sir,
Yes.
what was the point of us making a equal to e to the power c?
Oh, just to simplify, just to make our constants look nicer.
So,
That's it.
if you take the limit, aren't you gonna get PC to infinity? Ah, no,
No,
because no. Yeah, I see it. You're gonna get PT.
the
Yes.
constants will
Yes.
cancel each other out,
Yeah,
right?
I know. Yes.
Okay, so let's talk about this function for 1 second before we move on to some other stuff. Fernando, you mute.
Oh, sorry.
No, that's okay. So we had our logistic model is then given by, so a logistic model is what it's called. You don't need to know this term, but it's a relevant term. So our logistic model is given by some constant, so a times some constant, a, which is some constant, times the total population, times e to the kt, all over 1 plus a e to the kt. Sometimes, I'll just say sometimes you'll see this in the form a times pt over e to the minus kt plus a, I believe, if I've done that correct. Yeah, sometimes you'll see it like that. I'm not going to use it because why not? I
Sir,
guess that,
are we doing populations because it comes up, or is it
yeah, it's
an
because
example?
it's an example, right? It's an example,
Okay.
but it could
I
also
just I just
potentially
thought
come
it
up.
like it's part of the syllabus.
No, it could come up on an exam, right? They could say
Okay.
like a certain blah 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 is
Oh,
given by
okay.
this
Worded
function.
like okay.
Yeah. But of course they'll probably give you the differential equation. They won't make you come up with it on your own, right? But you could be required to solve the logistic model, for example. It wouldn't be an unreasonable question at all. It actually wouldn't be uncommon. I think I've seen it before, right? Okay, so if we wanted to set a particular initial population, so say we have initial conditions that p of 0 is equal to some constant, right? So in our case, this would be like 7,000. Then we would say, okay, plug that in. So we get p of 0 is a pt over just 1 plus a, right? And so if we set this equal to p0, this is what I was saying to Javier, I think, because you were asking me what the meaning of C was. Well, here we're going to find A. So we're going to get A pt equals 1 plus A p0, which is just a constant. We're going to try and isolate A. So we have A pt equals p0 plus AP0. And then we're going to get our A terms on one side. So we get A times pt minus p0 equals p0. And so our A is p0 over pt minus p0. So it's really not that easy to interpret, right? It's like the proportion of the initial population divided by the difference between the total and the initial population, right? That's not that easy to interpret what this means, but of course you can use this now, right? So let's say that there was one person in the world who was initially infected with coronavirus. That would be p0 is equal to 1. Pt would then be 7 billion for the population of the United States, of the world, right? And so we'd have our A is 1 over 6,999,999,999, right? Which is a really ugly number. But then we can use that, plug it into our equation, and what we're going to see, if we were to plot this, I could do this in Desmos, but there's not really a reason to, because I know what it looks like. What we're going to see is, this is going to look something like this. We have our P0, this is P0, and it's going to look exponential, so it's going to grow really rapidly like this. There's some point over here, which is called the point of inflection, right? So this is a point of inflection. You guys should know what that is. And after the point of inflection, it's going to stop being exponential growth. It's actually going to look more like exponential decay. And it's going to look something like that, right? And I think it was Fernando who pointed out this is going to be asymptote at PT, right? Because, of course, your population can't exceed PT, right? So you're going to get closer and closer and closer to PT. Now, this particular model, Peter, to answer your question, this particular model, there's no reason to know this particular epidemiological thing, right? But the point is that you can use regular old separation of variables to solve a very, very real and important situation, a question, right?
And sure, the curve that they used to put in El Telediario when we were in quarantine, it was new infected, the y-axis, right? Not infected.
Yes, yeah. That was new infected. There's been a few, right? So a lot of the ones that like Telediario, I'm pretty sure it was new cases versus time, but you'll also see ones that are like overall cases versus time and so on. And so this one is looking more like the overall cases, right? But of course, in our model, not only is it the overall cases, it's also the current ones, because we haven't included any possibility people dying of the virus or recovering from it, right? So that would be something else you have to include. Yeah.
So I'm a bit confused. Why are we finding A again?
Oh, we didn't need to. I was just saying if you wanted to find your initial conditions, if you had an initial condition, then you could find what A is, right? But I was actually only doing that because Javier had asked, what does A mean? And I was trying to show him that it's actually not that clear what it means, right? It's a proportion.
Okay.
Sir,
Yes.
integrating this will give you a interesting solution, like a graph.
So, like integrating this graph? Well, yeah. So if you integrated this graph, it would tell you basically the area under this, which you could interpret as being, let's see, if you're talking about total population. Yeah, so if you were doing total population, this would not be that interesting. But if you were doing new cases, then taking the integral of that curve would give you the total population infected. Does that make sense? But because we're already doing total, it's not really that enlightening what it gives us. It gives us population time, right? Which is not necessarily that. I don't know how to interpret population time, that unit of measure. But anyway, like people time. I don't know what that means. Maybe you guys can come up with an interpretation. I can't. All right. So this is what we were doing yesterday. I mean, we didn't do these specific real world examples, but we were using this technique of separation of variables, right? Basically everything on this page we did yesterday. So we have a function, let's say a derivative equal to a function of p and t, or a derivative dy dx equals a function of y times, remember that's very important that it's multiplication, times a function of x. Then we can separate by using division or multiplication. We can integrate both sides and abuse chain rule to make it solvable, right? Basically. So it's extremely important that we understand that this is only doable when it's f of y times g of x, right? So let me show you an example of something that, I hate when I do that. So let me show you an example of something that is not separable. So if we have the function dy dx equals y plus x, this is not separable. This is not a separable differential equation. And if you tried to separate it, so remember that our first step is always to get y terms on one side, x terms on the other side. So if you tried to separate this, we'd end up with, so say like we'd end up with dy dx minus y equals x. And if we took the x integral of both sides, which was our second step, right? X integral of both sides would give us dy dx minus y dx equals integral of x dx. So over here we'd get, we can separate this dy dx minus integral of y dx equals integral of x dx. But of course what we're going to get is y minus the integral of y dx equals integral of x dx. We don't even understand what this means, right? Because we have mixed variables, right? We have y and x in the same integral. We can't solve that integral. And so this isn't going to do anything for us. Yeah.
What if you, in step one, instead of doing step two integrating, you took the derivative and then do that into the differential function?
Say it again?
If in step one, instead of your next step doing the integral, your next step would be taking a derivative, and you
Okay,
get a new.
so if we took a derivative instead, what we'd end up with, we haven't even talked about what second order differential equations look like, but we'd end up with d squared y dx squared equals dy dx equals 1. And then, of course, we could, or yeah, equals 1, which then what would we do? I thought it was going to equal 0, but it doesn't even equal 0. So then what do we do?
Yeah.
Finn,
Y equal 1.
Okay. Yeah. There's no way.
Not
So
all
y
of
is equal 1.
Finn, where
Okay.
are you? I don't understand.
Library.
Really? It's so loud?
It's very chaotic.
Sir, but why does it
I'm
equal
going
1?
part.
Sorry?
Why does it equal 1?
I mean, this was a Fernando's suggestion to take the derivative of the first equation. Right? It's not going to help us. Right? But he was saying, what if you took the first derivative instead of taking the integral? What if you took the derivative to try and simplify your solution? Well, the derivative of x is 1.
Right.
Right? But anyway, the point is here, we don't have the techniques to solve this yet, right? So that's what I'd like to get to today is how we solve this equation, right? Because this is solvable. It's not separable, but it's solvable. So here's an interesting thing that you can do. We have no idea how to solve it, but we can still draw it, right? I can actually still show you what this thing looks like. I can't solve it right now. We can't solve it as a class, but I can show you what it looks like. How's that? Well, let me just draw it. I'll show you how I draw it. This is an interesting thing that you can do, right? This is called a slope field or a gradient field. So I guess you guys would call it a gradient field. In the US, we'd call it a slope field. What we're going to do is we're going to say, well, we know what the gradient is of this curve at any coordinate x, y, right? Because we have the derivative. The derivative is dy dx equals y plus x. So if we're at the point, so let's make a little table of values. And what my table of values is going to look like, it's going to be a 3-column table of values. I'm going to have an x column, a y column, and a dy dx column. So if I just start plugging in values, so let's say I plug in the origin. If I plug in the origin, I get 0, right? If I plug in, let's say the point 1, 1, I get the value 2. If I plug in, well, maybe I should start with 1, 0. So I plug in 1, 0, I get 1. Then I plug in 0, 1, I get 1. If I plug in 1, 1, I get 2. If I plug in 1, 2, I get 3. If I plug in 2, 1, I get 3, and so on, right? So I can come up with all these different values. And what I can do is I can draw a tiny little line segment at each one of these coordinates that shows me what the gradient should look like, right? So at 0, I'll do these in a different color.
You could draw a little point like with a differential length.
Exactly, yeah. So I could do at 0, 0, I have a little line segment that's got a gradient of 0, okay? At 1, 0, I've got a line segment that's got a gradient of 1, so it looks something like that. I made these a little bit too thick. I'm going to decrease that pixel size a little bit. So this has got, there we go, 0. 0 is a 0 gradient. Then I've got a 1 gradient. And then at, let's say, I'll just go over one more, to 2, 0. I didn't draw 2, 0 in there, right? So 2, 0, I'll have a sharper gradient. So it's going to get sharper, gradient of 2. And 3, 0 is going to be sharper still, so more vertical, and so on. So as I move over to the right, this line here is getting more vertical. And then I could go up to 0, 1. So 0, 1 is going to be just like 1, 0. It's going to be a gradient of 1. And same thing, as long as I keep going up in the y gradient, my thing is going to get sharper. So this would be 2. This would be 3, 4, so on and so forth, right? And then 1, 1 was 2. So 1, 1 is 2. 1, 2 was 3. Right? And so on. And then let's see, 2, 1 is also 3. I can keep filling these in, right? These are all getting sharper as I go up like this, and so on and so forth. Let's see, 2, 2 is 4, so it's sharper still. So these are also going to get sharper like this. These are all going to get sharper as we move out, right? I might be doing them a little bit exaggeratedly, but doesn't matter. And then let's see what happens if we move to the left. So if we start filling in the table of values, I'll keep it going like this. But let's go negative, right? So if we go to the left, my first table is much prettier than my second table. So if we go to the left, we could do things like minus 1, 0, minus 1, minus 1, or 0, -1, -1. You do -2, 0, -2, 0, -2, -2, and so on, right? You do -1, -1 is -2, -1 and 1 is 0, right? -1 and 2 is 1. So I can keep filling in these values as much as I want. I don't even really need to make a table because it's just addition, right? I can do addition. So if I move farther and farther to the left along the x-axis, I get steeper and steeper negative gradients. So this is going to look something like that's -1, then -2, then -3, then -4, so on and so forth, right? And I could go along, let's say the line y is, or x, yeah, y is equal to 1. Along the line y is equal to 1, I'm going to have a gradient of 0 here, right? And then it's going to start getting negative, right? So then it's going to start getting negative. So 1.
This looks kind of like
Kind of like a what?
a quadratic.
So it could potentially look like a quadratic, right? You're right in the sense that like it looks like it's symmetric about the y-axis, right? Or not necessarily symmetric about the y-axis, but there's some symmetry here, right? Or like anti-symmetric in a way.
Sir,
Yeah.
could you do a scalar field with this?
That's kind of what we're doing a gradient field, right? So every point is, or every line segment is represented by a scalar quantity, but there you can think of them as being like direction vectors. They're telling you which direction to turn in, right? Okay, so we can keep going. So I'll go along the line y is equal to 2. So here we'd have a gradient of 1, and then we'd have a gradient of 0, right? And then it would start going negative, right? So on and so forth. Okay. Okay, then one more point here. And then we could have here a gradient of 2 first, then a gradient of 1, then a gradient of 0, and
Are
then
they
a gradient of
symmetric
-1.
through the line y is equal to -x?
Sorry?
Are they symmetric through the line y is equal to -x?
Sorry, what?
Are they symmetric through the line y is equal to -x?
The line of, well, it's not, they're not symmetric. They're like, well, okay, they're symmetric because it looks like this, but it's really like anti-symmetric if you think of the value, right? Because one is positive, one is negative. But yeah, I see what you're saying. Yeah, and yes, that would be true. Yeah, that's exactly right. Because that's the line in which it's going to cross 0. When y is equal to -x, you've got -x plus x in your derivative, and it's 0. So all of those are going to be 0. So you can think of it actually like that way. All of these that are on the line y is equal to -x have a gradient of 0. Yeah, that's exactly right. And basically our gradient is going to flip-flop on either side of them. Okay, so I'm telling you what the gradient looks like at each point, but how does that tell us anything about the curve? Well, if we have an initial condition, so say we know that y, or when x is equal to 0, y is equal to 1, let's say, right? What that means is we're starting at the point 0, 1, and we just follow the gradients. So whatever this curve is should look something like this. Let's see if I can trace it out better. Okay. Right, so we don't exactly know what the equation for it is, but we can draw it, right? We can draw it relatively well. It might not be perfect, but of course, now I've been using integer values. I've been using 0, 0, 1, 0, so on and so forth, but there's nothing stopping me from doing 0, 0, 0, and then 0.0000000000001 0, and then 0.00000000020, so on and so forth. A computer could do that relatively well. And so you can imagine that using this technique on a computer, I could draw a really, really accurate graph, right? And yes, Fernando, yes, this is a family of solutions. That's exactly what this is, right? This gradient field is representing the gradient of all of the solutions, right? Well, in this particular case, it's all of the solutions that have, integer values, but you get the idea, right? It's an abstract representation of all the solutions kind of at the same time. That's exactly right. Yeah. Okay, so this is not a very practical method, right? Because we don't want to have to, first of all, just drawing this picture, and I haven't even drawn that many lines, is a pain. And I also did not draw this very accurately, right? I think you guys can probably see that pretty easily. This is not a very accurate picture. It's just based on my sketches, right? And even if I use a computer that does this really accurately, I would like, if it's possible at all, to know exactly what this function is, right? a formula that's y in terms of x, so I can plug arbitrary x values in and it'll spit y values back out, right? I'll say this, that not all differential equations are solvable, of course, right? This is one that is. And so we're going to develop the theory right now for solving this type of differential equation, okay? But let's start, before we do this one, let's start with one that we actually are equipped to solve already, all right? So let's try and solve a differential equation that I'm going to show you is solvable. And I think I briefly showed you an example like this at the end of our period last lesson, but I want to do it a little bit slower and a little bit more carefully now because I think I just really quickly threw it at you. So let's say we've got a differential equation that's in the form, I don't know, let's say dy dx. Oh, I still have purple going on. So we'll say, let's try to solve the differential equation. I'm going to have to modify it a little bit as I go, so give me a second. So dy dx, we'll say, I don't want to make it too crazy, so I'll just say sine of x. Here, we'll put a cosine of x here. No, other way around. We'll do a cosine of x here. We'll do a sine of x here. And here we'll do a, yeah, let's just call it a y for right now. And then we'll say this is equal to e to the x. Okay, so I'm claiming to you that we already know how to solve this differential equation. Well, we might not know how to solve it yet, but we have all the skills required to solve this differential equation, right? And the only way that I know that is that I designed it this way, right? But we can actually do something really exceedingly clever on the left side of the equation that makes this equation solvable, right? So as it stands right now, we don't know how to solve this because this is not separable, right? We cannot get all the y terms on one side and all the x terms on the other side by only using multiplication and division. It's impossible, right? So what we're going to do, and I mentioned this to you guys last time, is we're going to notice that this right here is just product rule. What is the product rule of?
It's sine y times sine of x. Right?
Not quite. Wait, what did you say, Fernando? I'm sorry, I can barely hear you. What did you say? Yes, sorry, I heard sine of y, sine of x. Yes, you're right. So this is just the derivative of y times sine of x. That's the left-hand side, right? So think about how we did implicit differentiation, right? Doing implicit derivatives or just using product rule on this would have given us, well, the derivative of y, which is dy dx, times sine. And then we do plus just regular old y now times the derivative of sine, which is cosine. Okay, so that's really clever, right? And this seems like it's a really special case, and it is. This is a very special case. This is not always going to happen, right? I could easily write down a differential equation that does not follow this pattern, right? So even the differential equation that we just studied a second ago, dy dx is equal to x plus y. If we brought y over to the other side, dy dx minus y equals x, this is not product rule of anything, right? So this that we're doing right now is a special case. It's a very special case, right? The left-hand side of this differential equation that we did before is not product rule, right? You cannot write it down as product rule yet. We'll get there. So this doesn't work. But now what we can do is we can say, so,
wait, sir.
Yes.
So we came to the conclusion that the derivative of y sine x is equal to all of that.
Yeah, and it was given to us by God, right? We're just getting really lucky and being very observant and noticing. I mean, in this case, I did it by design, but we're noticing that we can group these terms somehow as product rule, right?
Okay.
Wait, sir, we didn't learn the proof for it, right?
No.
we
We don't need a proof, right?
It's intuition.
Oh,
It's an observation.
it's just like the basic principle.
Yeah, it's like by the product rule, we're going to reverse engineer the product rule, but only in this case, because we're lucky, right? So in other words, let's see, let's generalize this. If I've got f of x g of y, right? Well, if I just have f of x times y, right? Yes, is there a question?
Yeah, in the exam, would we be expected to notice this, or would they say like they state
Don't
something
you
to do
worry
with the
your
product?
little head. We're gonna come up with a very foolproof method which makes you not have to think.
Okay.
Okay. Although I will say that if you can notice it early on, sometimes it'll save you time, right? But we're gonna come up with a method that makes it so that you don't really have to think about it. Okay. We'll get there. That's the whole point of the lesson today, I hope, is to get to we're gonna solve every single linear first order ordinary differential equation, right? But we'll get there. All right, so what we're going to say then is that this is true. This is just a fact from last year, right? That if I've got, well, from last year for you guys, not for the rest of your class, that if we've got the derivative of y times f of x, this is, of course, just equal to f of x times dy dx plus, let's say, y f prime. Okay? And so anytime we have a differential equation that's in this form, we can reverse engineer it, right? Okay, so in this particular case, we have it in that form. And so how do we solve it? Well, we can then rewrite. So we rewrite our ODE. Our ODE. So I don't have to rewrite the whole thing, although it may have been just the same amount of characters to write down that sentence, right? So we're going to rewrite our ODE as d by dx y sine of x equals e to the x. And so whenever we've got something like this, we've got a derivative with respect to x on the left side and a function of x on the right side, we can integrate, right? We can integrate this very easily. So we're going to just plop on an integral. And what we get on the left side is trivial, right? The left side is just going to give us y sine of x. The integral of a derivative is the function itself, right? And on the right side, of course, we just get e to the x plus c. Right? Everybody following me so far?
How's the derivative of y sine x e to the power of x?
Oh, assume we have some model that tells us that.
Oh, okay.
Right? Okay. And actually, to answer your question, we're about to find out what y would have to be if that were true.
Okay.
Right? And so if we wanted to find y, all we have to do is divide by sine of x. So we end up with, I'll move it up here. If this model is true, then we have y equals e to the x over sine of x plus c over sine of x. Okay? This is our general solution to that differential equation. But remember that we're lucky here. We're lucky that it's in this form. Not all differential equations, like that one that's got a big x through it, will be solvable this way, right? So this is a lucky thing. All right, so one thing to keep in mind, this is a really important thing to keep in mind. I can't believe that I haven't mentioned this to you yet, that anytime you find a general solution, so keep in mind that anytime you have a general solution, you can always check to see if your general solution is right? So we can check. Can easily check the general solution by just seeing if we plug it into the equation, if it gives us the right thing, right? So this is kind of a pain of one, but we can easily calculate dy dx, right? And plug in to our original OD. Right? So what I mean by that is we calculate dy dx, we plug both dy dx and y into our original ordinary differential equation, and we should get e to the x that comes out, right? If it doesn't happen, then we've done something wrong, right? I'm not going to do it here because I don't really feel like finding the derivative of e to the x over sine of x plus the derivative of c over sine of x, but you could easily do it, right? And this is a really important thing. Sometimes you'll see a question on an exam that's only worth 1 mark, and it'll say something like, show that blah, blah, blah is a solution to the differential equation. All you have to do is plug it in, right? You do not have to solve the differential equation to do that. All you got to do is plug it in, right? We'll do examples of that when they come up. Right? Don't worry about it right now. But this is an important thing to keep in mind. So,
Sir, can you stay on this for a sec?
yeah, of course. Yeah.
Okay.
So just, yes, yeah. Or you could write it as e to the x cosecant and do product rule, right? Whichever one. Yeah, but you're right. You'd have to do quotient rule, which is kind of a pain, right? But you can do it. It's procedural. You don't have to think.
But I don't understand why would you have to do anything else? You already have y in terms of x and your constant. What else do you have to do?
Just check and see if you got it right.
Ah,
That's what I'm saying. It's a way to check your general solution. You don't have to do this. This is if let's say you take an exam and you have spare time and you want to make sure that you got the right answer, right? Then you
Sure,
would do
but
this.
by dy dx, do you mean dy dx of the whole equation?
Yeah, yeah. I
So
mean, remember that dy dx represents literally the derivative of all of y,
okay,
right? Yeah, so in this particular case, it wouldn't be very fun to do it, but it's not hard, right?
but
As
like,
long as you remember your derivative rules, you're golden.
oh, okay. So what we found y, and then we just find the derivative of that, and then plug into your ODE.
Yep. Yep. You plug in
Okay.
y. You plug y is equal to e to the x over sine of x plus c over sine of x. You plug in dy dx is equal to whatever the derivative is into the left side of your equation, and then you should get e to the x back out. And if you don't,
Okay.
you've done something wrong. Right? So that's why I'm not doing it, because it's a ton of algebra. Right? And I'll do it in another example that's maybe a little bit nicer looking. Okay? Are we good with this?
Yep.
Awesome. All right, so let's develop a little bit more theory, because this is great. I mean, if we have differential equations that look like this, we're done, right? This is simple. But of course, we know we're not going to always have equations that look like this, right? That's really easy to see. You're not going to always have equations that can be really, really quickly written as product rule. If that were the case, we wouldn't need to be studying differential equations at all, because we just solved all of them, right? And it was super easy. So what we're going to do is we're going to develop a method called I don't know how to prefix this, but we're going to develop what's called the method of integrating factors. Okay, and integrating factors are really important, very, very important. All right, so this is called method of integrating factors. I think this is such a brilliant idea. I don't know who came up with it, but whoever did was, era-defining genius. Let me just check my battery. Okay. All right, so this is the method of integrating factors. So here's what we're going to do. I'm going to tell you right now, we're going to solve. So we're going to solve all linear first order ODEs. Okay? We're going to solve all of them. So all linear first order ordinary differential equations are going to be in the form, I'll write it like this: a of x dy dx plus b of x y equals c of x, right? Where a of x, b of x, and c of x are functions of x. Okay? This is what we're going to do. We're going to solve all of these. And so what typically is done, let me just make sure that I get the notation consistent with your book really quickly. Take 2 seconds. Yeah, PQ. All right. So what is consistently done is you make an observation that solving this differential equation is equivalent. So it's equivalent to solving the same differential equation, but we divide everything by a of x, right? So we're going to divide everything by a of x. I'll tell you why we don't have to worry about division by 0 in a second. So it's equivalent to solving this right here. So we don't have to worry about dividing by 0 here, because if a was 0, it wouldn't be differential anymore, right? It would just be a regular equation. So if we're only interested in solving differential equations of the first order, a is not 0, right? So this is justified. We can do this. And so typically, and what you'll see in your book, is they'll write this. They'll say, let, p of x be b of x over a of x. And let q of x be c of x over a of x. And so really, to solve all first order linear ODEs, all we need to do, so we just need to solve a much nicer looking differential equation, which is dy dx plus p of x y equals q of x. Okay? This, we haven't even started solving it yet, right? But I'm just saying these are two equivalent problems. The second one is much easier, right? So we're going to solve or much easier looking. So we're going to solve the easier looking one. So as long as we can write, any linear first order ODE in this form, we're going to be able to solve it at the end of this lesson, okay? And the way that we're going to do it is by using integrating factors. And it seems right now like I've done that example we just did a second ago where we found product rule. It seems like I've kind of abandoned that. That's actually the whole foundation behind this technique. All right. So I promise everything that we've done so far is relevant. Everybody okay with what we're doing? What our goal is to solve this equation?
Yeah.
Yeah? Okay.
I don't really understand our goal.
Well, we're just trying to solve a certain type of differential equation. And the certain type of differential equation is the one in this form, right? And this is going to allow us to solve differential equations like the one that was dy dx equals x plus y.
Okay.
Right? We're just trying to solve for y, right? We're trying to get rid of the derivative and just solve for y, basically. Make sense?
Yep.
Okay. All right, so let's dedicate a page at least to this. We're going to say our goal now is to solve dy dx plus p of x times y equals q of x, where we just remember that p of x and q of x are any functions of x, okay? And so what our strategy is going to be is to try and force this. We're going to try and force this to be in a form where the left-hand side is product rule, right? We're going to force, so let's force, well, try and force the left-hand side to look like product rule. And I'll just say this right now. This is not something that I would expect you guys to be able to just do off the top of your head, but once you've seen it, I would, right? So the way that we're going to try and force the left-hand side to look like product rule is by multiplying by some function of x, which we're going to call an integrating factor, okay? So we're going to multiply. So to do this, we're going to multiply by a function of x. We'll say some unknown function of x. Function of x, which we call an integrating factor. It's called an integrating factor, and we usually denote it, so denoted mu of x. Okay, mu of x is the one that I usually use. I don't know if your book uses mu or if it uses f or something different. I like mu because it stands alone, right? You don't usually use mu as a function, right? So I use mu of x. So we're going to multiply our entire equation by mu of x. All right. So if we multiply our entire equation by mu of x, so our new equation will say our new ODE is, I'm starting to get my lag already. Our new ODE is mu of x dy dx plus mu of x p of x y equals mu of x q of x. Okay? That seems kind of ugly. Why have I done this? Well, because if I haven't defined what mu is, right? Mu is just some random function, right? It's a random function. I have no idea what it is yet. If I can find a mu that makes the left-hand side of my equation product rule, then what I can do is I can rewrite the left-hand side as being product rule, and I can integrate both sides, right? That's the idea here. So what I'm going to do is I'm going to say, we want this to be product rule.
Mu of x is it just e to the power of x?
Not necessarily. Not necessarily. Mu's got a nice form. You'll see it in a second. It's kind of weird looking, but it's got a nice form. So we want this to be product rule. So what that means is we already have the y part being product rule, right? But what we want is for mu of x, for its derivative to be equal to mu of x times p of x, right? Let me show you what I mean by that. If mu of x prime, so if mu prime of x equals mu of x p of x, then we'd be able to write d dx of mu of x times y as, well, mu of x times dy dx plus mu prime y, which of course would be mu of x dy dx plus mu of x p of x y, right? Which is what we want. So if this is true, if we can find a mu of x that satisfies this, then we can write our left-hand side as product rule. Does everybody see what I'm talking about so far?
Not really.
Not really?
Me neither.
Which part's throwing you off?
The one. Wait a sec.
But like, you're trying to choose a function that when you derive it, it's gonna be itself times the function we've been given.
Yeah. Not when you derive it. Yeah. So you're trying to find a function. You're trying to find it. I haven't even told you how to find the function yet, right? Just keep that in mind. We're trying to find a function where when we multiply the whole equation by that function, on the left-hand side, it gives us product rule, right? And so we have just said that if such a function exists, it must be the case that its derivative is equal to mu times p, right? Because otherwise, the left-hand side wouldn't be product rule. I have not told you how to find mu yet. Remember that. So,
But does a mu exist for every single differential equation of this type?
For all differential equations that we are going to want to solve, yes. For all solvable first order ODEs, yes.
Okay.
Yeah, or linear ODEs, there will be one. I'll show you how to solve it in just a second. We actually already know how to solve it.
So the only two types of ODEs is separable and these?
Oh, no. The only types of ODEs that you will be studying this year are these. Or first order ODEs, right? We'll also be studying second order, linear, ordinary, homogeneous, and non-homogeneous differential equations, but we'll get to that later. That's the next chapter. For right now, we are only going to be studying linear first order ordinary differential equations, okay? And for linear first order ordinary differential equations, we are always going to be able to find a function mu of x that gives us this property. But for now, we haven't even talked about how we find it. Let's make sure that we understand everything that's written in red, okay? So let's recap. Our goal is to find a solution to every differential equation of the form dy dx plus p of xy equals q of x, right? P of x can be any function of x, q of x can be any function of x, right? So if we want to try and find the solutions to that differential equation, right, then our method is going to be to take some other function that we have not defined yet, multiply the entire equation by that, and try and make it so that whatever function we multiply by gives us product rule on the left-hand side. Right? And the reason we want to do that is because we just talked about an example. Let's see, where was it? We talked about an example right here where if we have product rule on the left-hand side, we can pretty easily solve this differential equation, right? Because we can just rewrite the left-hand side as a derivative and we can integrate derivatives, right? Integrating derivatives is super easy. We just cancel out the derivative, okay? So if we can force our equation to have it just be one derivative on the left-hand side and something on the right-hand side, right, then we're going to be able to solve this differential equation. And so what I've said here is we multiply by this function, okay? And multiplying by this function, if it's going to give us product rule on the left-hand side, it must be the case that the derivative of the thing we've multiplied by is itself times p, right? Because if you look at the left-hand side, right, if you were to try and reverse engineer product rule there, you would have to have a function of x times dy dx plus f prime times y. Remember, that was what we did in the previous example, right? anytime you've got something that looks like this, where you want it to be a derivative of, you're trying to do product rule, you have to have the underived function of x times dy dx plus y times the derived function, right? It's got to look like that. And so if we want to force that, all we're doing is we're saying our equation has got mu here and mu p, right? This is what we're looking at. And so if this is our equation, it must mean that this right here is the derivative of mu for it to be product rule. Does that make sense? Guys?
Yeah.
Uh,
To me, it kind of like, like when you started, I didn't really get it, but now kind of came full circle, so I kind of get it.
Okay, good.
as you saying, like that seems logical, but okay.
We haven't talked about how we find it yet, okay? And that's the next thing that's coming up. And I promise you that we already know how to find mu. I promise you. And we'll do a real example of this in a second so we actually see how this is working. I promise. I promise. It's not going to all be theory, but we need to develop the theory because this theory is always going to work for our problem. So we need to know it. All right. So what we essentially need to do then, so what we need, our problem has changed again to finding. So we need.
Now we just have to solve another differential equation
Exactly.
which is separable.
That's exactly the point. You got it. That's exactly what I was hoping to hear. So we now need to just solve the differential equation mu prime equals mu p. Right? And what I'm going to do is, instead of writing mu prime, I'm just going to write this as d mu dx equals mu, or I'll say, yeah. How do I write this better? Yeah, no, okay. D mu dx. Wait, hold on one second. Let me make sure that I write this better. Yeah, okay. D mu dx. Sorry. D mu dx. I just want to make sure that the notation is good. Equals mu times p of x. Okay. And what I'm going to do here is I'm going to separate it. I'm going to get all the mu terms on one side and all the x terms on the other side, right? Just as we did before. So this is going to give us 1 over mu d mu dx equals p of x. And then to solve these types of differential equations, all I've got to do is integrate. So I'm going to integrate 1 over mu d mu dx with respect to x and integrate p of x with respect to x. Now, I'll say this much. The right-hand side of this equation cannot really be simplified because p of x can be any function of x, right? I don't know what the integral of p of x is. There's no one standard formula for finding integrals, so we're just going to leave it as integral of p of x, okay? But the left-hand part of the equation turns into just a mu integral, right? It's just 1 over mu d mu. This is just by using separation of variables. And of course, that's just natural log of mu. Again, I'm not too worried about constants here, okay, or absolute value. So we get natural log of mu is equal to the integral of p of x dx. And so if we wanted to find mu, we would just write mu equals e to the power of the integral of p of x dx. Okay. So I did that kind of fast. Did anybody get lost in that part?
In that part, no.
Good.
But I still don't get what we're trying to do.
All right. So it's about to come full circle. I'll show you. What if mu isn't linear? What do you mean by mu not being linear? It doesn't matter, right? It doesn't matter what mu is. As long as you can find, it's a product, right? So anytime it's a product, you've got it in a separable form. So it doesn't have to be linear. Mu could be, if you wanted it to be, it could be mu squared, but it's not because we've designed it so that it's just 1 power of mu. We've designed it to be linear. Does that make sense? Because we're just multiplying by mu, and so pretty much by construction, mu is going to be linear. Now, if your ODE is nonlinear, so if you have y squared, this might not work, right? But we're not dealing with those differential equations. Those are much harder. Right? So we're just dealing with the case where the ODE itself is linear. All right, so Anastasia, what were you asking? You were asking, you said you understood the mu thing, and then you didn't see what we were trying to do overall,
Yeah.
right? Okay. What if mu of x is quadratic? Yeah, there's no problem with mu being quadratic. That would mean that it's e to the power of the natural log of x squared somehow. So you'd have to have an
Okay.
integral whose solution is natural log of x squared.
Another part I don't understand is that on the left side, after you wrote if that, and then underneath you did the derivative of mu x y. What is that? Why are we doing that?
That's showing you that the whole point of that was to show you that if we want the left-hand side of our original ODE to be product rule, then that means mu prime must equal mu times p.
Okay.
This is just showing you why. This is the reason for why
Sure,
this
yeah.
has to be true, right?
Okay.
Okay. All right. So let's try and do some recap really quick before we go forward anymore, right? Just a little bit of recap. So what have we done so far? So far we started out with a differential equation of the form dy dx plus p of xy equals q of x. And we said multiply by, so step one was to multiply by mu of x. So that gave us mu of x dy dx plus mu of x q of x, or p of x, sorry, y equals q of x mu of x, mu of x q of x. And we said force the constraint that mu prime equal mu of x p of x, right? Which this leads us to finding that mu of x must equal e to the power of the integral of p of x.
But sir, can you hear me?
Yes.
What about if mu? Can you go to one slide back? So if mu isn't linear, like it's a quadratic, the integral of 1 over mu isn't going to be natural log of mu.
Say it again.
So if
Yes,
mu,
Fernando, listen. You're doing separation of variables. So no matter what happens to mu, you're canceling out your x integral. You're just doing an integral with mu.
oh yeah,
Right?
okay, yeah,
Right?
yeah.
Make sense?
Yes.
Cool. All right. So we said that if we force this constraint, we end up with this integrating factor mu of x, which is e to the power of the integral of p of x, right? So let's see really quickly what happens, right? Let's just see what happens. So we'll say observe. I'll do a side note in blue, right? Observe that if we actually multiply this through our function, take the derivative of mu prime, or take the derivative mu prime, this would be e to the integral of p of x, right, times the derivative of the integral, right? So times d by dx of the integral. I know this looks really ugly. Right? Times the integral, which is just p of x. So this is equal to integral e to the integral of p of x times p of x, right? But remember that this was how we defined mu. So this gives us mu of x p of x. So I'm just confirming, just keep in mind that all I'm doing here is I'm confirming that the derivative of mu is in fact equal to mu times p, right? Everybody okay with that? And so what that does for us is it tells us then, so now we can say a third step is we can rewrite the left-hand side. The left-hand side, mu of x dy dx plus mu of x p of x y can now be written as d by dx, just the derivative of mu of x times y, right? Because doing product rule here, so I'll say because, I'll make sure that's understood, because this would equal mu of x times y dy dx, sorry, plus mu prime of x y, which is of course equal to mu of x dy dx. plus mu of x p of x times y. All right? Everybody follow that?
Yes.
Okay. And so our fourth step is then, I'll say our fourth step is now to recognize that we have a new ODE. Our new ODE is just going to be d by dx of mu of x times y equals mu of x q of x, which we can now solve, right, by just taking the integral of both sides. So we get mu of x times y equals the integral of mu of x q of x, right? And finally, we can isolate y, right? Y is just going to be equal to 1 over mu of x times the integral of mu of x q of x. Okay? Where, of course, we remember, so with mu of x being equal to e to the power of the integral of p of x.
So to solve one differential equation, we've had to solve three of different ones.
Pretty much. I mean, we've really only solved two because we changed one, its format only. And then we actually solved one and solved another one. So we have to solve two. Yeah, that's right. Okay, so I know that this is all hard to follow when it's just a bunch of abstract stuff. So let's do a specific example. Keep in mind, guys, that what we just wrote down, this is so unusual. It's hard for you to to emphasize enough how unusual it is to find one formula that spits out a solution. This never happens. So this is a really, really awesome thing. Yeah.
In our first step, this is what we derived from the last slide, right?
Mm-hmm. Yep.
Okay.
Yeah, the number 1 and 2 is all from the previous slide.
Mm-hmm. Okay.
And then number 3 is what we do with that information, basically. Well, number 3 and 4 is what we do with that information. So let's actually solve a differential equation, a real one, so we can see that this actually works. It's actually going to give us a solution, right? It's not just some random thing that I'm doing. Okay, can I move off of this slide? Or you guys need a second?
I would just like to ask, how many marks would a differential equation of this type put?
Well, you'll see that once you start doing them, it's pretty procedural. So not as many as you might think. 5 or 6, right? You'll see when we actually start doing examples that you don't have to repeat this theory each time. You need to know it. You definitely need to know it, but you don't have to repeat this exact same theory. You can start, for example, by using the fact that mu of x is equal to e to the power of the integral. Right? You can do that straight off the bat. I would advise against just using this formula, just because there's first of all a lot of things to remember, and sometimes if you're not observant, you might end up wasting a lot of time that you don't need to do. Right? There are certainly some questions I've seen in FP2 where they make it look like you have to use an integrating factor, and it turns out that you can just use product rule. Right? So they tend to be a little bit tricky sometimes that way. They're conniving, but you in theory you can just jump straight to this, right? I will say that it's not, I don't advise that, but you could in theory do that, right? Let's do a problem and let's see how this actually works with a real problem. Let's see the problem that we were talking about before, right? So we were saying that we couldn't before, so let's solve now the differential equation dy dx equals x plus y. Okay? So to solve this differential equation, what we basically need to do is we need to put it in the form. So we need to first put it in the form. So put in form. I'm starting to get lag. We need to put it in the form dy dx plus p of x, y, equals q of x. So to do that, it's really easy. We just subtract y from both sides, right? So that's just going to be dy dx. I'll write it over here to the left. Dy dx minus y equals x, right? And so we have a p of x that's just minus 1, and a q of x that's just regular old x. Everybody okay with that so far?
Yeah, more or less.
Okay. Well, that's okay.
How do you wait? Oh my god.
Okay.
Okay. How do you choose your px and qx again?
It's not by choice, right? P of x is always the thing that's multiplied by y.
Yeah, right.
Got it?
Yeah.
Cool. All right. So what I'm going to do for this problem and this problem only is I'm going to multiply through by mu, and I'm going to basically repeat the theory. But I wouldn't have to repeat the theory every time. I'm going to do it right now so that we can see explicitly how this theory is working. Okay? Because it's clear to see that the left-hand side is not product rule, right? That's very clear to see. But it's not clear to see how the mu thing forces that to be product rule, right? Because there's a lot of variables basically that are going around in the previous slides. So what we're going to do is we're going to just repeat the theory. So we're going to multiply by mu of x, which is going to give us, I'm getting so much lag, mu of x dy dx minus mu of xy equals mu of x q of x, which is just x, right? And so we said we wanted to force it. We want to force mu prime of x equals this thing, right? Whatever comes in front of y. So in this case, that's minus mu of x. All right. So what that's going to lead us to is that mu of x equals the integral, or e to the power of the integral of p of x. Do you guys want me to repeat how that's true? Or is that okay?
Could you just repeat what mu of x is?
We don't know right now. We're about to find it. Right? But we're multiplying by some function that's going to hopefully allow us to get product rule on the left-hand side, right? That's what mu is. It's called an integrating factor for that reason. We're trying to make it so that we can put it into a product rule and integrate, right? So if we let mu of x be defined by e to the power of p of x, or e to the power of the integral of p of x, we would get that mu of x is equal to e to the power of the integral of, well, just minus 1 dx, which is easily seen to just be e to the minus x. Now I'll say here that you don't actually need the constants. So technically there's a plus c here, but you can always ignore it because that's just going to give you different versions of mu. So just take the easiest one, which is when c is equal to 0. All right. So
Wait,
do you know? Yes.
How's the derivative of mu equal to minus mu x?
Well, let's take a look. If mu of x is equal to e to the minus x, what is the derivative of mu of x? Well, the derivative is just minus e to the minus x. What is that? That's just minus mu of x. Right?
Okay.
So forcing that constraint is what defines mu, basically, right? We're defining mu through a differential equation. Okay? And so if we have minus e to the minus x as our integrating factor, then if we multiply our differential equation, so if we take mu of x dy dx minus mu of x y equals mu of x x, multiply or putting in e to the minus x gives us e to the minus x dy dx minus e to the minus x y equals, let's say, I'll do the x first, x e to the minus x. Okay, so all I've done is I plugged in my mu. And so if you notice, the left-hand side is just the product rule. Cut that off. It's just the product rule of e to the minus x y. Right? That's all it is. It's the derivative of y times e to the minus x plus the derivative of e to the minus x times y, which is exactly e to the minus x dy dx minus e to the minus xy. Right? And the right-hand side is just x e to the minus x. Okay, so far so good. Everybody okay with this so far?
Mm-hmm.
All right. All right, and so integrating gives us e to the minus xy equals the integral of x e to the minus x dx. Right? So we have to solve that integral. How do we solve that integral?
Or I can't remember how it was called.
Integration by parts.
Yes.
So in
Wait,
integration,
why
Huh?
are we doing the derivative of e to the power minus x
we're
times
not
y?
doing that derivative. We just said that the left-hand side of this differential equation can be written as that derivative.
Oh,
And
okay.
that's the whole point of this method, right? So
Mm-hmm.
when we do the inverse power rule, hold on, look what did Javier ask. Let's see what Javier asked. I think when we do the inverse power rule, constant c doesn't matter.
Sir, I meant when you were doing mu is equal to e to the power of the integral of p of x dx, you didn't put the plus c, so I was asking if it was at the end or the
So
Um,
Hello?
F in the
Thank
chat, boys.
Pensaba que se me había caído a mí. Pensaba que se me había caído a mí. La cosa no era que
hello?
Hi, sir.
I don't know what happened. Anyway, I'm back. All right, so hold on. Let me rejoin real quick.
So the plus c.
Oh my god. Can you guys not hear me again?
No, I can hear you. I can hear you.
You can't, because it says se ha
Yeah,
perdido
it's
la
okay.
conexión a la red. It says I've lost connection again. Is it okay? Can you guys hear me and see me?
Yeah, we can hear
Yeah,
you.
we can hear you, but yeah.
All right. So, oh god, I don't know what's happening. My Wi-Fi is always usually really amazing. Okay. Very frustrating. Okay. Let's go back. So, what I was saying before I got cut off. Can everybody hear me?
Yeah, perfect.
Yes.
Okay.
Yeah.
All right. So what I was saying before I got cut off was the reason we don't need to include the plus c in our mu, in our integral inside of our exponent, is because we're picking any mu that satisfies this differential equation, right? So pick the easiest value of c. Pick c is equal to 0,
Oh.
right? It doesn't matter what we let c equal. It can be anything. So it doesn't matter. It's, mu is not part of our solution. It's just the thing that's going to help us get our solution. So pick any of the mu's that'll work. There's an infinite number of mu's because it's a family of solutions. So pick the easiest particular solution, basically. And you could see that if you included a plus c there, your plus c would carry through the entire thing and not matter. It would cancel off because in our solution we divide by mu, right? We divide by mu and we multiply by mu in our integral. And so we'll have a product of our constant in our integral and a 1 over that constant outside of our integral. And so they'll always cancel off.
Okay. And
Right?
could we, if it would be easier, could we do something like c is equal to -2? It will make the problem easier.
Sure, yeah, you can choose any one that you want. Any of them will work. That's true. I don't think there will ever be constants that make it that much simpler than just using 0, but you're certainly allowed to. Without a doubt, you're allowed to. Choose any C's that you want. Okay. So, it seems like you guys are struggling with this a little bit, so I'm going to go through it again, what we've done. So we've said, we started off with the differential equation dy dx is equal to x plus y. We're going to put it into the form dy dx plus p of xy equals q of x. To do that, all we've got to do is bring the y terms on one side, right? And now we're allowed to use subtraction and addition because we're not doing separation of variables, right? We're not trying to do separation of variables. We identified our p of x to be the thing that comes in front of y, and we identified our q of x to be the other function of x, basically, right? Once we've got it in that form, we are going to multiply the whole equation by some function who's, that we don't know yet. We don't know what the function mu of x is. We're just going to say multiply by mu of x and make it so that mu of x must have this constraint such that its derivative has to be equal to the thing that comes in front of y, because doing that allows us to write the left-hand side as product rule. That's the whole method here. Nothing more difficult than that, okay? We're just saying multiply by mu and force mu to have this extra condition, this constraint, that makes it so you get product rule on the left-hand side. If you can find one of those mu's, if you can find a mu that does that, you can solve the differential equation, right? And so the way that we define mu to make that happen is we say let mu equal e to the power of the integral of the thing that comes in front of y. Because no matter what you do, if you can find a mu that satisfies that equation, it will turn into product rule on the left-hand side. Right? That will always, always, always be true. Is that much clear?
Mm-hmm.
Could you repeat the what make it equal to what did you just say? Could you repeat like the thing that you just said, like about the that's always true?
Yes. If you can find mu of x equals e to the power of the integral of p of x, if you can solve that integral, if you can find a mu that way, right? If that mu exists, which it will for all of FET problems, then the left-hand side of your equation will always become product rule. It will always be the derivative of mu of x times y.
Oh, okay.
Right?
Okay. Because I think I cut off.
Okay. Oh, okay. So that's the way that we're constructing mu. We're basically defining mu to be the function that gives product rule on the left-hand side. And so if we can find mu, right, then we can solve the differential equation, right? Okay, so now we're at the point where we've done that. We've written the left-hand side as product rule, and then we've integrated, right? And what we're left with right now is trying to find this integral of x e to the minus x, which requires integration by parts. And so I'm going to do integration by parts really quick. The integration by parts I'm going to use is u is equal to x, dv dx is equal to e to the minus x. So this is where I was saying it's helpful to know your integrals, right? And so du dx is just 1, and v is minus e to the minus x, okay? All right. And so our integral is then going to be uv minus the integral of v du, right? That's our integration by parts formula, which is, of course, going to give us minus x e to the minus x minus the integral of v du. So I'm going to get a minus the integral of minus e to the minus x. So I'm going to put a plus there, e to the minus x. And then it's dx, right? Because du is just 1. And this is going to give us minus x e to the minus x minus e to the minus x. And here we do need to add a plus c, because this is actually an integral in our solution. Okay? And so we're left off with e to the minus x times y equals minus x e to the minus x minus e to the minus x plus c, right, plus c, which if we divide both sides by e to the minus x, give us y equals minus x minus 1 plus c over e to the minus x. Okay? Everybody okay with that so far? Guys?
Yeah.
Yep.
All right. So let's take a second let's just go over what we've done today, right? And I want to show you something that has come full circle, all right? Let's go over everything that we've done. So we briefly recapped separation of variables, right? It seems like people are somewhat comfortable with this method. Separation of variables is very, it's lagging. It's very formulaic, right? You always do the same thing. You divide, only can use multiplication and division, but you divide and multiply to get all the y terms on one side, all the x terms on the other side, and you basically make use of chain rule, right? So basically, using chain rule, you can take the integral with respect to x of both sides. The left-hand side becomes a y integral. The right-hand side becomes an x integral, right? And then if you can solve those integrals and you can make y the subject, you're done, right? That's the whole method of separation of variables. Then we talked about some particular examples, right? So we said you could have bacterial growth modeled, and you end up with an exponential decay or exponential growth formula, right? And physics people, you should recognize that formula. You've probably seen that a billion times. Or chemistry, biology people, you've seen it too, I would assume, right? Okay, and then we talked about a correction to that model, which is called a logistic model. These were just two basic examples of separation of variables, okay? Then we had a blank page. This was the graph of our logistic model, still part of the same example. And then this is the part that I wanted to get to. We talked about a differential equation that we do not know how to solve, right? This differential equation was dy dx equals y plus x. We had no idea how to solve it, but we could, and I showed you there that separation of variables will not work, right? That's those little integral things. It gives us something that's nonsense. But what we can do is we can construct a table of values, and we can draw a picture of our function, right? It's not exactly what our function is going to look like precisely, and definitely doesn't give us a formula for our function, but it gives us a rough idea of what it looks like, okay? So that was what we did there, and I want to come back to that in just a second. Then we did a really special example. This special example was a differential equation where the left-hand side, by design, was automatically equal to the product rule, right? And so what we can do is we can reverse engineer the product rule and say the left-hand side of this equation can be written as d by dx of some product equals a function of x. And since we just have a derivative equal to a function of x, we can just integrate both sides and solve, right? And as long as the integral on the right-hand side is solvable, we're golden. We can do this integral, no problem. Or we can do this differential equation, no problem. Okay? And then we said, what if we could make that even further? We could go even further with that and apply that to differential equations where the left-hand side doesn't look quite like the product rule. And that led us to the method of integrating factors, which is basically to say any function of the form a dy dx plus by equals c, right, can be rewritten in a form dy dx plus py plus q, right? And what we did then, I'll move on to the next page. What we then did is we said, what if we were to multiply this by some random function? We don't know what it is. We multiply it by the whole equation. We multiply it by something. And we multiply it by something that makes it so that the left-hand side is product rule, right? If we could find such a function, then we could solve this differential equation, right? And we showed that if this function exists, right? If this function exists, so in other words, if we can write the left-hand side as product rule, then that would have to mean that mu prime, the derivative of mu, is equal to mu p, right? And because that's just how product rule works, right? You have a derivative of one function times the other, plus the derivative of the other function times the original one, right? And so on the left-hand side of the left-hand side, we have mu of x dy dx, which means we've taken the derivative of y. So the other term would have to be the derivative of mu times regular old y. So mu of x, p of x has to be the derivative of mu if this mu exists, all right? And then once we've established that mu has to be, a function such that mu prime is equal to mu p, well, that's a separable differential equation. It's separable because it's just a function, mu times another function, right? So whenever we've got multiplication of functions, those are separable because separation of variables means multiplication and division. So we separate that by dividing by mu and then integrating with respect to x, which turns our left integral into a mu integral and our right integral into an x integral, just like separation of variables.
So
Yes.
at the bottom right corner where it says mu equals, it's mu of x, right? It's just you don't want to carry.
Yeah, exactly. It's mu of x, Mm-hmm. And so we show through this method of separation of variables that mu has to equal this e to the power of the integral of p of x, right? Which is kind of a strange looking formula. But the thing is, we don't have to repeat this process anymore, right? Now, I recommend repeating it, but I don't recommend repeating our derivation from mu, right? I think that repeating the right-hand column here where it says we need, repeating that every time is a waste of time. You don't need to do that. I would recommend repeating, I would actually multiply through by mu and rearranging, but I wouldn't recommend having to, mu is always going to be equal to e to the power of the integral p of x. It's always going to be true, right? It's always going to be true. And if you want to remember why it's true, just remember that it's separation of variables, okay? And so once we've established that that's what mu has to equal, then we can rewrite the left-hand side. I'm moving down to point 3 now here. We can rewrite the left-hand side as a product rule, right? Because that's how we designed mu. Mu is designed to obey the product rule, right? And so that means once we've established what mu has to equal, we can write it as the product rule, right? And once we can write the left-hand side as the product rule, then we've got a differential equation in the form derivative equals function. Whenever we've got derivative equals function, we can integrate. And so we do integrate. And the integral and the derivative cancel each other out, and we're left with just the thing on the inside of the derivative. And on the right-hand side, we have an integral that we do need to solve, right? We might not be able to even solve that integral. But if we can solve that integral, we've solved the differential equation, right? And so we have a general solution that will always, always work, which is astounding, that will always work as long as that integral is solvable. We will always have y equals 1 over mu integral of mu q, right? That will always, always be the case, which is incredible. It shouldn't be that way. It's very rare that we get so lucky in math where we have a solution to all equations of this form, right? But we do. And so we did a specific example, and this is the last thing I want to talk about. We have a specific example where we are going back to that one equation that we tried to solve pictorially, right, by drawing little gradients at every point, right, pictographically, and we just solved it analytically. In other words, we actually used this method of integrating factors to find an actual solution, a general solution to this problem, right? So what I want to show you is that we can actually plot this in Desmos, right? And we actually recover, well, assuming that my picture wasn't horrible. Where is Desmos? Where do I have Desmos on here? There we go. All right, so our solution was y equals minus x minus 1. Let me go back. Minus 1 plus a constant. I'll plug in the constant over e to the minus x. So I'll just write it like this, times e to the x. Right? So I need to add a c. And so our c before, it looked like our in our
Sure.
original. Yeah.
I'm confused on one step.
Go for it. Which part?
We defined mu prime as being mu times p, right?
Yes.
So then, in theory, you can define mu as being mu prime divided by p.
I mean, sure. But then we don't know what mu is because it's still mu prime in terms of mu. Or mu still in terms of mu prime.
Then if we plug in that mu, it would the p's would cancel and we would only have mu prime, so we won't have product rule.
What? No, you wouldn't. You would have mu dy dx minus mu prime.
Yeah.
But that's still a differential equation with two unknowns. You still have mu and mu prime. And they still would have to obey the same constraint. You would still get product rule. It's just written in a different form.
Mm-hmm.
You see what I'm saying? Because you still have mu and mu prime. Right?
Yes.
It's just product rule written in a different form. You're not seeing what I'm saying, are you?
No.
Okay. So if you're talking about right here, if instead of actually solving for mu, you wrote instead mu is equal to mu prime over p, right? Then you'd end up with the equation mu dy dx plus mu prime.
It's just what I don't understand is how we're just plugging in mu x and mu x everywhere and we're gonna get product rule. Because okay, I understand you have
but listen to me. Hold on, listen. We are
but
designing.
Is dy dx the derivative of px?
Javier, listen to me. We are designing mu. We're not just plugging it in. We're designing mu to be a function that forces our differential equation to be product rule. It's by design that we're doing that. We're doing that on purpose. That's the whole point. The whole point is we don't have product rule. Let's force product rule to happen.
I know, but like, what is dy dx? Dy dx with respect to what?
dy dx. What do you mean with respect to what? It is the derivative of y with respect to x. Okay. Let me see if I can write this out in some words. The point, right? Whenever we've got differential equations like dy dx plus p of x y equals q of x, our goal is to find y. is to find
Right.
y.
I thought the whole p of x function included the y.
No. P of x, that's the
Right,
whole.
right,
The
okay.
only reason this will work is because P of x is only an x, right? Whenever we've got a differential equation like this, our goal is to find y. Think of it as being dp dt equals kp, right? Our bacteria population model, and we're trying to find the population at any given time, right? That's the same thing that's happening here. We have dy dx, blah, blah, blah. Our goal is to find y
It
in
makes
terms of
sense.
x.
It makes sense.
Okay.
I got very confused. Like I included the y into the p of x function. So
No, so
everything was getting very messy.
P of x and Q of x have to be only functions of x. If they're not functions of only x, then it's no longer linear, right? And we don't have techniques to solve nonlinear differential equations right now, right? So it's specifically a function of x times y, right? That's the only reason that we're able to do this. And so what we're saying is, to solve this, we force it to be product rule on the left-hand side. That's why the mu comes up, okay? All right, so really quickly, I know that I'm keeping you guys a little bit extra. If you notice, like I could stretch this a little bit. I think it was like passing through 1, 0, so maybe it would be like right there. Right? So if you notice, my God, it's so laggy. Let's type it in. 2, more or less, looks like. So it looks like this equation right here is passing through the point 0, 1, right? And if you notice on our picture that we had drawn before with just our little gradients, we got a really similar looking thing, right? So it's justifying in two different ways. Sorry, it's lagging a little bit. In two different ways, it's justifying that we've done the right work here, right? We've did this little picture and we got this picture here, right? And by solving it analytically, we're getting something that looks really similar, which is telling us that we probably are on the right track here. And it turns out this is right. This is the correct solution. Okay. So we'll obviously do some more examples of this tomorrow because it seems like this is giving you more trouble than I thought it would. That's okay. I mean, it is very weird at first. One of the advantages of previous years is that I've had a lot more time to do calculus with students in year 12 because you guys had very few lessons last year, as you all know. And so my year 13 students usually have a really strong base in calculus, which means that none of the calculus confuses them at all. And so they can just focus on the new material. And I do understand that you guys also aren't masters in calculus. So anytime we're doing calculus, you have to think to yourself, why is that working again? Why is that working again? Oh yeah, that's working. So there's an additional thought process there. But my point is, try and go through your derivative rules at least to make sure that you can understand the product rule argument here. That's the really important thing here. Product rule and chain rule are like the two most important things for our differential equations topics, both of them. Right? Chain rule is especially going to be important later on when we talk about substitutions, right? We're not doing that right now, so don't worry about it. Tomorrow, what I'd like to do, we had said originally that we were going to do some problems. So I'll ask you guys if there's any problems that you want to do from any of the other things that we've done. And then even once we're done with that, I want to just do a bunch of examples of differential equations with integrating factors, okay? So tomorrow's an example day. So don't stress about it being anything new and crazy. And then the new and crazy stuff will come later. All right. Are there any questions about anything?
No. The only thing is that
No.
I think that like derivative stuff I'm pretty solid with, but it's just with integrals I still have to think quite a bit when doing
Same.
the
Well,
use of
that's
it.
I mean that's never going to go away, right? Everybody's got to think about integrals. You're never going to be able to look at well, you might, but you're not going to look at an integral like x e to the minus x and go, oh, I know what that equals. You're not going to be able to do that. So that's why I've been doing the integrals in blue, because I want to show the steps for the integrals.
Sir, for
Right.
this, do we need to do the I can't even speak right now, integration and differentiation of P4?
So technically, yes, you would have to. I mean, we did a lot of that in the beginning. So all the stuff that you need for these two chapters is the stuff that we did in the first 4 lessons. So you have it all. Just the practice is obviously the biggest obstacle, right?
Because I did the chapters from P3, but not from P4 yet.
So I think that the big gap that you'll have if you haven't done the P4 ones is the integrating. I don't think the differentiation will be difficult,
probably.
but the integrals are all there. But I wouldn't worry too much about it. I mean, definitely do it if you have time, but don't stress about it too much because I'm never going to do integrals quickly. I'm never going to
Okay,
just say,
sure.
other than U substitution, I might do U substitution quickly. I'll never do an integration by parts quickly. It'll never happen.
Okay.
Okay?
Then see you tomorrow.
All right, guys. I'll talk to you tomorrow. Have a good afternoon or evening.